Welcome to Lecture 4 of the Rad Sound Mammography Physics Comprehensive Guide. Okay, so we've built the physics, we've walked through the equipment, now we ask the question that really matters most. And this, right here, this is the fundamental conflict in all of mammography. You've got this relentless, driving need for an absolutely perfect image to find the tiniest, most subtle cancers. But on the other hand, you have an ironclad responsibility to keep the radiation dose as low as you possibly can. So, let's dive into that tension.
Everything in mammography really comes down to this constant, inescapable battle between three key factors. And we call this the quality-dose triangle.
Think of it like this. You're trapped. On one side, you need incredible spatial resolution to see those tiny microcalcifications. On another, you need fantastic contrast to pick out subtle masses. But fighting against both of them all the time is noise, that random, grainy static that just wants to obscure everything. And here's the trap. Anytime you try to improve one of these, you usually end up paying a very steep price somewhere else.
There is just no free lunch in this system. Look at how this works. Say you want sharper resolution, so you use smaller pixels. Well, now each pixel catches fewer photons, which means more noise. So how do you fix the noise? You have to crank up the number of photons, and that means a higher dose. What if you want better contrast? You use lower energy X-rays, right? But more of those get absorbed, so you have to increase the dose again just to get a usable image. It is a constant, unavoidable trade-off.
Okay, so let's dig into those first two corners of our triangle, resolution and contrast. The demands here in mammography are they're unlike anything else in radiography. We are truly, literally trying to see the invisible. Just look at these numbers for a second. To reliably spot microcalcifications, we need a resolution of 15 to 20 line pairs per millimeter. That's how many tiny distinct lines you can cram into a single millimeter and still tell them apart. To put that into perspective, a standard chest X-ray, that only needs about 3 to 5. We are playing a completely different game here.
So how do we actually measure this insane level of detail? Well, the gold standard is something called the modulation transfer function, or MTF. It's basically a score for how well each part of the system, the focal spot, the detector, reproduces the contrast of what it's imaging. But here's the absolute kicker. The total system MTF isn't an average. It's the product of all its parts. That means your imaging system is only as sharp as its weakest link. One bad component drags the whole thing down.
Now for contrast. And this is where it gets really, really tough. The natural, inherent difference in X-ray absorption between cancerous glandular tissue and the surrounding fatty tissue is only about 15%. That's it. This is the lowest subject contrast of any imaging exam we do. It's like trying to find a polar bear in a snowstorm.
And this brings us to the metric that truly matters in the clinic, the contrast-to-noise ratio, or CNR. Because, it doesn't matter how much contrast a lesion has if it's completely buried in noise. CNR is what tells us if the signal, the potential cancer, is actually strong enough to rise above all that static and be seen. And that leads us right to the third corner of our triangle, and really the main villain of our entire story, image noise. This is the thing we are constantly fighting against. Now, there are 4 types, but let's be honest, quantum noise is the big one. It's just the inherent randomness of how X-ray photons hit the detector. Then you have what's called anatomical noise, which is sneaky. It's not really noise at all. It's just normal overlapping breast tissue that can perfectly mimic a lesion. And the crucial thing to remember is you can't fix anatomical noise by throwing more dose at it. The only way to sort that out is with a different technology, like tomosynthesis.
Okay, everybody, listen up. This right here is one of the most famous and punishing relationships in all of medical physics. Because noise is related to the square root of the number of photons, if you want to double your signal quality, you can't just double the dose. You have to quadruple the radiation dose. This is a classic exam trap for the FRCR, for your boards, you name it. And it's just a brutal physical reality we have to deal with.
So how much signal-to-noise do we actually need to see something? Well, there's a rule for that. The Rose criterion tells us that for the human eye to reliably, consistently detect an object against a noisy background, the SNR has to be at least 3 to 5. If it's below that, it is physically invisible. It doesn't matter how good the radiologist is, you just can't see it. So, we're trapped, right? It sounds hopeless. Better resolution costs dose. Better contrast costs dose. Lower noise costs a ton of dose. So, is there any way out of this trap? Well, yes. There is one hero in this story. There is one way to break the triangle.
And it's called detective quantum efficiency, or DQE. DQE is the ultimate measure of how good a detector is, plain and simple. It tells you how efficiently that detector takes the X-ray photons that hit it and turns them into useful image information without adding a bunch of its own noise. Basically, a detector with a high DQE wastes fewer photons.
And this chart, this just brilliantly shows you the digital revolution in a nutshell. Old school screen film systems, their DQE was about 25%. They were literally throwing away 3 out of every 4 photons that hit them. Modern digital detectors, they have a DQE of over 60%. This is why digital mammography completely took over. It wasn't because of better resolution, it was because of this massive, massive leap in efficiency. It let us get a better image for the same dose, or an equivalent image for a much lower dose.
So, now that we understand all this physics, how do we actually apply it? How do we take these principles and use them in the clinic, day in and day out, to make the best possible image for every single patient?
Believe it or not, the single most powerful tool we have is compression. Why? Because it's the only thing that improves everything at the same time. It makes the breast thinner, which lowers the dose. It spreads the tissue out, which improves contrast. It brings everything closer to the detector, which improves resolution. And it holds the breast still, which gets rid of motion blur. It's a win, 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 win.
Okay, here is another classic exam trap. People think that by fiddling with the window and level on their monitor, they're improving the image quality. You are not. Windowing just changes the display. It changes how you look at the information that's already there. It absolutely does not improve the underlying signal-to-noise ratio. You cannot create information that wasn't captured in the first place.
This slide is just a fantastic summary of everything we've talked about. It's your cheat sheet. You can see all the trade-offs laid out so clearly, but look closely at compression and DQE. They're the only 2 factors here that give you a net benefit across the board, improving image quality while actually lowering the dose, or at the very least, holding the line.
So after all this physics, all these equations and graphs, what is the real take-home message? What does this all mean for our patients?
Well, it really comes down to this powerful quote from Dr. Jafar. In mammography, image quality isn't just some technical number, it's a clinical outcome. Every line pair we can resolve, every decibel of signal to noise we can gain, every percentage point of DQE, that translates directly into a real-world result. It determines whether a cancer is found at its earliest, most curable stage, or whether it's missed entirely. Getting the physics right isn't just an academic exercise, it saves lives.